So in today's lecture, we will introduce the Thevenin's theorem, Norton's theorem, and the concept of the maximum power transfer. So what does Thevenin's theorem say? Thevenin's theorem says that if you have a linear two-terminal circuit, this linear two-terminal circuit is made of resistors, sources, dependent, independent. You can find an equivalent circuit that is way simple in its topology, that is made of one independent voltage source and one single equivalent resistance that is connected in series to it. So if this is my linear two-terminal circuit, as I said, and this circuit is connected to the load here that this circuit is supposed to supply power to, I can find an equivalent circuit to this circuit. So if I am to say that this is my linear two-terminal circuit, where I have here voltage source or sources, current, dependent, several types, resistors, I can find an equivalent circuit to this complex that is made of several component circuit, that this circuit is as simple as a voltage source that is independent connected in series with a resistance that I'm calling R Thevenin, and this is V Thevenin. So this is what the Thevenin's theorem says. Now, here in this theorem, we have two cases we will be looking at. So as I said, this is considered a powerful technique in circuit analysis because it simplifies and finds an equivalent simple circuit that basically replaces this complex circuit and does the same job. Now, for us, in order to apply the Thevenin's theorem, we need to know how can we simplify this circuit. So back to here, if I have my circuit here that is connected to a load, so this is my circuit, this is my big circuit that I am connecting this circuit to this load. What I need to do first is to disconnect this load and find the equivalent circuit, the Thevenin's equivalent circuit, and then after I do this, I bring back the load again. So this is how we do it. If we have a load that is connected to my circuit that I need to simplify, I need first to disconnect this load, put it aside, find the equivalent circuit, and after I find the equivalent circuit, I put back the load. Sometimes I don't have, the load is already taken, disconnected from the circuit, so I can right away start finding the Thevenin's equivalent circuit. But if I have the load connected to my circuit, I need to disconnect the load from my circuit, simplify the circuit, and then put back the load. So, as I said, we have two cases for those linear complex circuits. It could be a resistor. It could be another smaller circuit. It could be whatever that load. It could be simplified or represented by a resistor, for example, as we will see in our example. This can be called a load. Like, for example, when you connect your light bulb to the outlet, your light bulb is the load that is, for example, represented by a resistor, for example. we will do an example once we introduce first the first case. So as I said, we have two cases to look at. The first case is related to the sources, which means I only have independent sources. So if I only have independent sources, then the first case is the following. If I have only independent sources in my circuit, then at the beginning I need to find the voltage at the output of the circuit after disconnecting the load. And this voltage is called V7. Again, the first case, which is considered the simpler case, is when I have no dependent sources. In this case, I will disconnect the load, and the open circuit voltage, we call it open circuit because there was a load and I disconnected the load from the circuit. So my circuit now became an open circuit at the output. At the output, I need to find the voltage at the output, and this voltage is now called the Thevenin, which is, I found this is the Thevenin. So what about the Thevenin? TH. So what about the Thevenin? If I have no dependent sources, again, which is that case number one, I need to switch off those independent sources and look at the output and find the resistance. As simple as this. So if I don't have dependent sources, only independent sources in the circuit, number one, I need to find the open circuit, the voltage open circuit, which is the Thevenin. And then I need to switch off all independent sources. And calculate the resistance looking at the output. Looking from the output, I calculate the resistance. This way, I find the Thevenin. We will see an example. So let's do this example. So here we need to apply Thevenin's theorem to find the equivalent circuit to the left of the terminals in the circuit, then find the current I. So usually we distinguish the output for a circuit with having such terminals here. Those terminals here tells me that this is now a load. This is my load. The 1 ohm resistor is the load that is connected to the original circuit. If I am to put the circuit in this box, so you can see now what do I mean. So this is the load. And this is my linear two-terminal circuit, okay? So I need to apply Thevenin's theorem to find the equivalent circuit and then find the current I. So what I'm going to do is the following. So at the beginning, I will disconnect the load from my circuit. So the circuit's going to look like this. I have the 12 volt, 6 ohm, 2 ampere. Notice that all the sources are independent sources here. 6, 4, and I will keep those ones just to show me that I have disconnected. Now this is an open circuit. This is the load has been disconnected. So I have here the open circuit. So I need now to find the voltage here. I'm calling it VOC, open circuit. This voltage will be the Thevenin's. So now I need to apply whatever circuit analysis, any of the circuit analyses that you have learned to find the voltage at the output of the circuit. For example, I can do a nodal analysis here. Put this one here as my reference. And then this is how let's do it the way we used to do. This is a node. This is a node. That's a node. And this is a node. However, if you recall, the node that is connected between the reference and the voltage source that is connected between the reference point and the node will result into the node being known, right? We don't need to write a nodal equation right here because now this becomes 12 volt. So this node is known. So what are the nodes that I need to write the nodal equations for? It is this one. I'm calling it V1. And this one that I am calling it also, let me use different color, just V1, V2. Now notice that V2 is VOC, right? But I just made it this way. So the same approach that you've seen earlier is not changing at the moment until you completely understand how are those variables related. So notice that here, V2, the voltage between node, this blue color, and the reference is the same as VOC, right? It is the same. So I have here V2, just for my record, I'm just writing it. V2 is the same as VOC, and this is also the Thevenin. VOC is the Thevenin, right? In this case, we need to, just for our record, so we don't get things mixed up. So now I need to calculate V1 and V2. I need to write the two nodal equations. So nodal equation at V1 as VOC is always equals to V Thevenin. It is always the same, right? Because this is the open circuit. The voltage open circuit is the V Thevenin. So they're always the same. Okay. So nodal equation at V1. So what do I have? I have -2. I have plus V1 minus 12 over 6. Keep counting the branches so you don't miss, right? So we have, look at the branches that are connected to V1 here. 1, 2, and 3. So I will end up with 2, 3. So V1 minus 12 over 6 plus V1 minus V2 over 6 as well, and this equals to 0. So I covered all the branches that are connected to V1. Now nodal equation at V2 is V2, how many? I have 1 and 2, so I have V2 minus V1 over 6 plus V2 over 4 equals to 0. It's minus 2 because the current is entering the node, right? The current is entering the node that I'm writing the nodal equation on. Okay, so now I need to rearrange those two equations. So if this is 1 and this is 2, so in this case, if I multiply the first equation, so 1 multiplied by 6, what do I get? So I get V1 minus 12 plus V1 minus V2 equals 2. Minus 2 is going to go to the other side, becomes 2. 2 times 6 is a 12, right? And then this one can be simplified further to be 2V1 minus V2 equals to 24. So this is 3. Now, the equation number 2, I can multiply by 12. So this becomes 2V2 minus V1 plus 3V2 equals to 0. Or rearranging minus 2 V1, 2 V2 plus a 3 plus 5 V2 equals to 0. So this is equation number 4. Now, if you add 3 and 4, as simple as this, so 3 plus 4. Go ahead, Matthias. What do I get?
I'm beginning to notice, sir, that are there many different routes to solving for variables in a circuit? Because I'm sure loop equations or nodal analysis could have helped solve this.
As I said, there are always several ways to solve for circuits, right? Nodal analysis and mesh analysis are one of the most powerful. We could have used superposition. We're doing nodal analysis right now. Yes. So V2 equals to 8 volts. Now take this one, 5, substitute V2 and 4, for example. Substitute 5 and...
Sir?
Yes.
I thought 24 divided by 4 was 6.
I'm sorry, my mistake. I'm talking to you and working at the same time. Okay, 6. Yeah. Okay, so substituting 5 and 4 is going to result into, I need to calculate V1. Then I have here V1 equals to 5 V2 divided by 2. And then V1 equals to 3 times 5, 15 volts. Right? Did I get this? 6 times 5 over 2, 3, 15 volts. So this is how we solve. We could have solved it using mesh analysis. No difference at all. We have to be careful. In mesh analysis, how you pick up. Here you would be having a super mesh. If you use this mesh and this mesh, you'll be having a super mesh, right? So this is probably another way to look at it, to try to practice solving and getting the same answer. So let me continue here. Okay. So we have now V1 as 15 volt, V2 as 6 volt, right? So we need the V Thevenin, which is V2. So we know now that V Thevenin is 6 volt. So we could have stopped at V2 equals to 6 volt because this is what we were after. We were after the V open circuit, which is the V Thevenin. Now the next step is, again, since we only have independent sources, we are going to switch off those sources. Do you recall what do we do to currents, independent current source and independent voltage source when we switch them off? So how do we treat the independent current source and an independent voltage source when we switch them off? No, not really. Not really. Not all of them. Yes, voltage source, we replace it with a wire. Current source with an open circuit, which basically as if we have removed it. So here, switching off, I will redraw the circuit again. So in this case, I have so this is a wire, and this one an open circuit. So I have 6, and I don't forget that I have A and B here. I still have the load disconnected, and I need to look from here, right? This is my R7 looking from here. So I have 4, 6, and 6. So what do you think? What is R7? Can somebody tell me what is R7 here? What's R7? So 6 and 6 RN. 6 and 6 RN series. Wonderful. So I'll do it in steps so you don't get confused or you see the bigger picture. Always remember the terminals that you are looking at. So what do you see? What do you see? What's the relationship between 4 and 12? That's correct. So always keep in mind, if you think that you would maybe get confused, just redraw or put the color those terminals that are to understand. Do you see the 12 and the 4 sharing both terminals? Absolutely. So keep in mind, we're finding the equivalent resistance. This right now, I'm only finding the equivalent resistance. If I put a voltage source or a current, yes, the current is going to be split into those two resistors. So here I have now 12 in parallel with 4. So R Thevenin, I will keep writing the T. It's up to you. You're going to write it small or capital, that's fine. So R Thevenin is 3. So now what is the equivalent circuit? The equivalent circuit to this circuit is as simple as a voltage source in series Now I will bring back the load, and I need to calculate this I. How much is this I? Look here. Don't you see 4 and 12 are sharing both nodes, both terminals? I am looking here between A and B. Right? I'm looking between A and B. What do I see? I see 4 and 12 connected in parallel. Isn't that right? Is it clear to you now? Absolutely, because they are sharing both nodes, the same nodes. Yeah. So back to here, I is 6 divided by 3 plus 1, and I equals to 6 divided by 4 as 1.5 ampere. Now, let's move to the next example where I have dependent sources. If I have dependent sources, then in this case, I cannot switch off the dependent source. There should be another way to find the R Thevenin. The V open circuit is going to be found the same way we have done it for the first case. We need to find the V open circuit, right? However, when it comes to finding the R Thevenin, I cannot switch off the dependent sources. Dependent sources cannot be switched off because they are not sources that generate power from themselves. They rely on other variables within the same circuit. So what do I do? In this case, I will need to do two things. I will switch off the independent sources. However, I will hook up a voltage source at the output or a current source at the output and either calculate. So I know this voltage, this is known. I need to calculate this. Or I know the current source and I need to calculate the voltage across this current source. And in this case, what is R Thevenin? R Thevenin would be this voltage that I know divided by the current that I calculated. Or this current that I know divided by the VO that I will calculate. So in other words, I need to find the relationship between a voltage and the current at the output while switching off the independent sources. So when I switch off the independent sources, I cannot find the R Thevenin the way I did it for case number one. I have to hook up a known source and calculate the withdrawn quantity. So if I put a voltage source that I know, I need to calculate how much the current would be withdrawn from this voltage source. If I put a current source that I know, I need to calculate how much would be the voltage drop across that source. And then R Thevenin is the ratio between this voltage to the current. Okay? So this is one of the ways. This is one of the ways. So let's see an example here. We have this circuit. We need to find the Thevenin's equivalent circuit to this. Notice that the load is already taken away. I don't have a load connected to that circuit. So I can right away find the voltage open, the open circuit voltage, right, at the output. So how do I do this? Well, this is the voltage, the V open circuit right here at the output. So if I put my reference here, if I do nodal, right? Or you can do mesh. It's up to you. Whatever you want works. In this case, nodal analysis here, when I have voltage sources, is basically reduces the number of equations because now the voltage right here becomes known. Why? Because I have a voltage source, an independent voltage source between the reference and this node. So the voltage here is 6 volt. So what do I need to do here? I need this voltage, V1, and this voltage, V2. And notice that V2 is VOC, and this is V7. So writing the first nodal equation, so I have nodal equation at V1. What do I have here? I have minus 1.5 Ix. I have V1 minus 6 divided by 5. I have V1 minus V2 divided by 3 equals to 0. So this is the first nodal equation. Count the branches. I have 1, 2, and 3. Nodal equation at V2 as V2 minus V1 divided by 3 plus V2 over 4 equals to 0. Now don't forget that we have Ix that came from this dependent source, we need to find a relationship between this Ix and my original variables, which are the V's, the node voltages. So what is the relationship between Ix and my node voltages? Looking here at the Ix, I can see that Ix is indeed V1 minus V2 over 3, right? So this is my Vx. So this one is 1, this one is 2, and this one is 3. Then substituting 3 and 1 to get rid of the Ix. One would give you minus 1.5 V1 minus V2 over 3 plus V1 minus 6 over 5 plus V1 minus V2 over 3 equals to 0. Right? Now rearranging and solving for V1. Now you have two equations, two unknowns. You need to rearrange. Now if you multiply by 15, you would get multiply by 15, so 5, so minus 7.5 V1 minus V2 plus 3 V1 minus 6 plus 5 V1 minus V2 equals to 0. Now rearranging here, I have minus 7.5 V1 plus a 3 plus 5 as 0.5 V1. I have 7.5 V2 minus 5 plus 2.5 V2, right, equals to 3 times 6, 18. Go to the other side. To 3 times minus 6 is minus 18. Goes to the other side, becomes 18. So this is the equation, right? Rearranging the second equation as well, multiply by 12. So what do we get? The second equation. So we have here, if you multiply by 12, you get 4 V2 minus V1 plus 3 V2 equals to 0. So I have here minus 4v1, 4 plus 3 plus 7v2 equals to 0. Those two equations. If you solve those two equations, you get the V open circuit. So what do we have here? Hmm. So we have here 0.5 V1, 0.5 V2 equals to 18. Okay, so if I multiply this with 8, right? If I multiply this with 8, what do I get? I get 4 V1 plus 20 V2 equals to 144. Again, you can solve it the way you want. Here in our dependent sources, we only have one extra relationship between our controlling variable and our standard variables. Once you substitute it into it, you reduce the number of the variables, becomes back to here in our case, two variables. So you have two equations, two unknowns. But let me now, if I add this and this, what do I get? I get 27 V2 equals to 144, and V2, which is my V Thevenin, is by 27 is 5.333 volt, and this is my V Thevenin. So this is the first 5.333 volts. This is my V Thevenin. In order now to calculate the R Thevenin, we have two approaches. The one that I have explained, which is hooking up a source at the output while switching off the independent sources. And there is a second approach, which is a general approach. You can find the short circuit by having a short circuit at the output. So I'll show you both approaches. The first one is the one that I told you about, which is to switch off. So switching off independent sources. And connecting a source at the output. Give this following. So you pick up the source that you want. For example, here, if I switch off this independent source, I end up with a piece of wire here. And then this will not be switched off, of course. Will stay there. 1.5 IX. Three, 4. And then here comes the output. What do you want to put? It's up to you. You decide. You can put a voltage source. You can put a current source. So if I put a voltage source, then this node is known. So let me put here a voltage source. I'll put a voltage source here. And I will give it the value of 1 volt. Okay, I stopped there. I did not continue. I did not solve V1 because I'm interested in V Thevenin. So I can stop at V2. Now here, I put this source. I added this source at the output, and it switched off the independent sources in the circuit. And I decided this voltage source to be 1 volt. Now, what do I need to do? I need now to calculate the current. The current that will be withdrawn from this source. I'm calling it I naught. Okay, so if I again do nodal analysis, yeah, I just give it a voltage of 1 volt. Yeah, that's right. I need to calculate the I naught. Okay, so nodal analysis, the voltage here is known now. This voltage here is 1 volt, so I don't need to write. I only need to write one nodal equation here. I'm calling it V. You're gonna call it V3. You're gonna call it again V1. It's up to you. Let me call it V3 just to be different. So I have only one nodal equation here to do, right? Because the voltage here at this node now is known. This node is known, right? I need to write the nodal equation here. And look at the ground. I just want to show you the ground when I switched off the voltage source. What happened? All those now are one node. All those are now one node, right? So I just need to, so this is 0 volt. I just need to write one nodal equation at V3. And this is what I'm going to do. So nodal equation at V3 as V3 over 5 minus 1.5 IX, right? Now this IX is different than the IX we did earlier, right? Why? Because there were some physical changes happening in the circuit. So if you want, just to avoid any confusion, you can put a prime here, just to make sure that you don't mix between this IX and the IX in the previous circuit, right? Then that's why I put V3, just to disconnect those variables. So you know now you have a new variable. This IX prime is different than the IX we did in the earlier circuit. And then what else? How many branches we have? We have 1, 2, and 3. So the third one is V3 minus 1 over 3. And now this equals to 0. Is that right? Now I need to find a relationship between Ix and my V3. What is this relationship? I know that Ix prime equals to V3 minus 1 over 3. Right? Just take this one and put it in here. What do you get? You get V3 over 5 minus 1.5 V3 minus 1 over 3 plus V3 minus 1 over 3 equals to 0. This is the equation that you need to solve. So let me insert here one more slide. Okay. So I have V3. If I multiply this equation by 15, what do I get? I get 3 V3, right? Minus, so 3 V3 minus 7.5 V3 minus 1 plus 5 V3 minus 1, right? Notice V3 the same V3 minus 1. So here I have minus 7.5 V3 minus 1 plus 5 V3 minus 1. This is going to result into minus 2.5 V3 minus 1 equals to 0, right? So 5 minus 7.5 plus 5 of V3 minus 1 is going to give you minus 2.5 V3 minus 1. And then now we can delete this. Simplifying this further is 3V3 minus 2.5 V3 plus 2.5 equals to 0. And now this is 0.5 V3 equals to minus 2.5, right? And now V3 is minus 5 volts. So we found V3 to be minus 5 volt. I need I naught. So what does this mean? What is Ix? Because now if you look here at this, let me copy this one and bring it. In order for me to find I naught, I need to apply a KCL here. So let me call this one, this is A, right? So this is A, this is B. So if I say KCL, and let me say that the current here is going this way, let me call this one I1, and this is CIX, IX is already entering. So I need to find I naught. So if I say KCL at A, what do I get? I get I naught is entering minus I naught. I1 is leaving plus I1. IX is entering minus IX, and this is equals to 0. So I naught is indeed I1 minus IX. How much is IX? What is the relationship? If you recall, we said IX equals to V3 IX, and let me put the prime here. So, prime, right? And the prime here. And also, if I don't have a prime here, I'll put the prime. So what is IX? IX is V3 minus 1 over 3. And we found V3 to be minus 5. So I will now, and what is I1? I1 is 1 volt divided by 4, right? I1 is 1 volt divided by 4. So I naught equals to 1 divided by 4. This is I1 minus, what is Ix prime? Ix prime was V3 minus 1 over 3. We know V3 is minus 5, is that right? So V3 minus 1 over 3. So here I naught is 1 over 4 minus 5 minus 1 over 3. So I naught is 1 over 4 minus 6 over 3, which is minus 2, times minus becomes plus 2. So I naught is 2.25 ampere. So what's our Thevenin? Our Thevenin is this voltage, the source that I put at the output, which is 1 divided by the I naught, and this is 1 divided by 2.25, and this is 0.4 R Thevenin, 0.444 ohm, right? Or 444.4 milli ohm. So this is the V Thevenin, this is the R Thevenin for a circuit that has dependent sources. So this is, again, one of the approaches. I'll leave the second approach for other examples that we will be doing. No, it's not going to change anything. If you put this as a 2 volt, you will notice that the I naught will increase. The I naught will become 4.5. Divide 2 by 4.5, you're going to get the same ratio. Remember, this is a linear circuit. So if you increase the voltage, the current will increase as well. This is the Ix prime. Here. So this is how we do it. This is how we solve it. This is one approach for the R7. We're going to talk about the second approach later on, but this is how we do it. Any questions so far about Thevenin's theorem? Again, to summarize it, there are two cases. First case is when we have only independent sources, and you've seen how we've done that. We found the voltage open circuit, and then we found the R7 by simply switching off those independent sources because there are no dependent sources. The second case, where we have a mix of dependent and independent. In this case, we cannot find our Thevenin by only switching off independent sources because dependent sources are going to stay there. They're not going to be switched off. So we have to put a source at the output and then calculate the other quantity withdrawn from that source. And then the ratio between the voltage and the current for that source that we added would be our Thevenin. So the Norton's theorem is not that different from the Thevenin's theorem. However, here in Norton's theorem, instead of finding the V Thevenin by calculating the voltage open circuit, here we will also remove a load. If we have a load here, we will remove a load. However, to find the Norton's equivalent circuit. However, the Norton's equivalent circuit is basically a current source, an independent current source that is connected in parallel with a resistor that is called R Norton. And by the way, this R Norton is equal to R Thevenin. So R Norton, R Thevenin, they're the same. The only difference is the representation for the circuit. In the Thevenin's theorem, the representation was a voltage source in series with a resistor. That's called R Thevenin. In Norton's theorem, it is a current source that is independent in parallel with a resistor that we call R Norton that is the same as R Thevenin. No difference at all. But how do we find the I Norton, the current, this independent current source? If you recall in Thevenin's, we used to calculate the voltage at the output, right? So this is the A and B for Thevenin's. We used to calculate the VOC, that we call it the voltage open circuit, and Thevenin. In Norton's, no, we don't calculate the V open circuit. We come here and we put a wire between those two terminals. In other words, we shorten the output. We put a wire to make a short circuit. And then we calculate this short circuit current. This short circuit current is the I Norton that will be later on represented by a current source. And then the resistor that we will find, I Norton, is the same as the R Thevenin. So those two circuits, they are related. As you remember, when we did the source transformation, we always used to transform a voltage source that is connected in series with a current source that is connected in parallel. So in other words, if I have the Thevenin R Thevenin, V Thevenin, and I have the Norton right? This is the Thevenin's equivalent circuit. This is the Norton's equivalent circuit. If you recall from the source transformation, if I do source transformation to this circuit, to the Thevenin's equivalent circuit, what do I get? I will get this one. Why? Because if you do the source transformation, basically this series resistor will be now transformed to parallel, and then a source, and this source is indeed V Thevenin divided by R Thevenin. And remember, we said earlier that this is R Norton as well. So this one is also R Norton. So this is the relationship between the Norton's equivalent circuit and Thevenin's equivalent circuit. You can get one from the other. So far we have seen how we calculated the V Thevenin. If you recall in the first two examples we did, we found the V Thevenin by calculating the V open circuit, right? And then I found the I Norton by calculating the short circuit, right? Now, and this is the general approach, the R Thevenin, which is also the R Norton, is indeed the ratio between the V open circuit to the I short circuit. And this is the second approach that I told you about. So instead of hooking up a voltage source or a current source at the output to calculate the withdrawn current, for example, the same way we did, we could have done the short circuit approach and then find the R Thevenin by taking the ratio of the V open circuit to the I short circuit. Because we've seen earlier here that the relationship between the I Norton and R Thevenin is indeed, so this is what? This is the I short circuit. And this is what? This is the V open circuit. So R Thevenin is the V open circuit divided by the I short circuit, which means that circuit that we hooked up a voltage source at its output, I could have shortened the output and calculate the short circuit there, and then find the R Thevenin to be the V open circuit that I already calculated divided by the I short circuit. So let's look at this example to find the Norton's equivalent circuit at the terminal A and B. So again, the same cases here. As long as I have independent sources, look what I'm going to do. I will come here and put a wire right at the output and find the I short circuit. Okay. Now, what's going to happen if I put a wire at the output? Any component connected in parallel with this wire would be completely out of the calculation, right? Why? Because it will be shortened. No current is going to go through. No current now is going to go through this 6 ohm. So let me now redraw the circuit after I have connected this short circuit at the output. Why? Because I want to calculate the I Norton. So now my circuit is going to look like this. Okay, I need the I short circuit. So how do I calculate the I short circuit? You know, do mesh analysis this time and have a supermesh. By the way, you can still avoid the supermesh. If you take this little one and you took the bigger one, you could avoid the supermesh. But let's do it with the supermesh, just for the fun of it. So I have here I1, I have here I2. Now notice that I2 is I short circuit now, right? So right, just here on the side, for you know that I short circuit is indeed I2. So I need to find I2. So if I am to apply the mesh equation at I1, so mesh equation at I1, what do I get? Now this is a super mesh, right? So I need to write the super mesh. It's going to be one super mesh. So super mesh, remember in this case, you can eliminate this current source and you can go this way. Now my positive is in the same direction. It's not going to, both of them are going clockwise, so they maintain the same direction. So now I can write minus 15 plus 3I1 now I'm done now. I'm done with I1. Now I move to the I2 plus 3I2 equals 0. Done. That's a super mesh. Now what is the binding? What is the binding equation? Remember, this is I1, this is I2, right? Which means that this one here is I2 and this one here is I1. And if you take the KCL right here at A, so KCL at A, what do you get? I1 is leaving, positive. I2 is entering, negative. 4 ampere is leaving, positive, equals to 0. Right? So I1 minus I2 is minus or. I would like always to write it. Then in this case, I2 minus I1 equals to 4. And here, what do I have? I have 3I2 plus or divided by 3. Divided by 3. What do you have here? You have I2 plus I1 equals to 5. Right? So this is 1 and this is 2. If you add 1 to 2, 1 plus 2, what do you get? You get 2I2 equals 9. Right? Or I2 is 4.5 ampere. And this is what I want. So I Norton is 4.5 ampere. Okay, time is over. I don't want to take more from your time. It's already 12:51. We can continue in next lecture what we have started today. If you have any question, you can leave if you want. If you have a question before you leave, would like to ask, please go ahead. We will continue in next lecture. Calculating the R Thevenin. The R Norton, which is the same as R Thevenin. It would be great if you practice those examples. As you see, since we started going into the superposition, nodal analysis, mesh analysis, things now are started to become a bit more difficult than KVL, KCL, those straightforward laws, Ohm's law. So you really need to practice. And I did not include the nodal and mesh analysis and quiz number 1 to give you the time, but please make use of this time. So any question? Go ahead.
Sir, where is A again for this new super mesh?
Okay, so here in the super mesh, we calculated the KCL right here at the node A in order to find the binding equation between my mesh currents and my current 4 ampere, because I1 and I2 are sharing this 4 ampere. And by the way, the material for quiz number 1 are already posted. And I can make sure. I did put an announcement, quiz number 1, first quiz, and I listed all the material covered in the first quiz. Please read the announcement. Please keep an eye on the announcement and all the updated material, uploaded material to the course link. And I will post the formula sheet very soon. So Matthias, did I answer your question?
So A would be here. I think I'll have to annotate for a moment. Actually, never mind.
Just a second. Let me open that for you. Yeah, go ahead.
So is that where A is when you say KCL at A?
Yes, that's correct. But here I removed the current source just to show you the super mesh. But this doesn't mean that the current source is not there. This is just for illustration purposes to show you where is the current source. But the current source is here and no difference at all.
All right, thank you.
You're welcome. Any other questions before we conclude our lecture? It's a current source. It is a circuit that is represented by a current source. Sometimes you need an equivalent circuit made of a voltage source with a series resistor. Sometimes you want an equivalent circuit that is made of a current source. And in this case, the resistor would be in parallel with that source. Remember the source transformations we've seen. You're simplifying a circuit down to a voltage source with a resistor in series, that's Thevenin's, or it could be a current source with a resistor in parallel. This is Norton's approach. And you can always go between Norton's and Thevenin's exactly the same way we used to do the source transformation. So if you, for example, want to calculate the Thevenin's, you could have gone that Norton's approach and then later on find the Thevenin's by dividing by multiplying the R Thevenin with the I short circuit or with I Norton. Any other questions? Okay. So I think, did I answer your question? Do you have other questions? No further questions. Please make use of the office hours, or you can still email me, whatever is convenient to you. Thank you so much, and have a good day.